Thank you very much, Steve. And I'd like to, first of all, convey my sincere thanks to the organizers, Greg, Connie, and their team, who've been absolutely fantastic and fabulous in providing the support. And no doubt the success that we see here today can be attributed to them. Certainly getting to the point where we are at in terms of the research that we do at the Smart Center is a whole bunch of people coming together, and I do want to again acknowledge the fact that there are students, staff, and equally importantly, industry partners who we work with, and I have chosen to talk about a particular industry partner, OneSteel, who has come together as part of this project that has now been running for many, many years. And the partnership with OneSteel is the reason why, indeed, this technology is commercially successful, not just here in Australia, but internationally. The technology has been implemented where we've actually taken waste tires and used that in the process of making steel. So yes, indeed, we've been able to successfully demonstrate that you can use materials like tires, plastics, to be able to manufacture high-tech products like steel and other kinds of metal alloys. And I'll give you a bit of a taste for that in the talk and how we actually achieve that. But I think the simple message here is that when we think about the 3 R's, the reduce, reuse, recycle, the thinking is, of course, we're assuming everything can be recycled in a traditional manner, which is converting glass into glass and plastics into plastics. The reality is that not all materials actually lend themselves to that type of transformation. So when we talk about using glass and transforming that into regular glass, you can achieve that in some instances. But the minute you start to get into the more complex form of glass, and I'll show you again some videos as to why they're difficult to recycle, what do you do with them? What do you do when you cannot convert glass into glass? The reality is you've got to start to ask, well, actually, what is it that makes glass what it is? So there are basic elements in glass like silicon and oxygen, so that's silica. And it's about recognizing the fact that a lot of these materials actually contain some pretty important elements. So if you start to actually dig deeper and look at elements like silicon that are present in glass, you actually realize that, gee, this waste is actually not waste after all. It's actually quite highly valued element like silicon, which is used in electronic manufacturing. So when you want to manufacture electronic products, you actually need elements like silicon and carbon. But the fact that we're actually throwing away and calling them as difficult to recycle materials is not because we don't want to recycle, it's because we actually don't know and don't have the science and the technology in terms of how do we actually transform it into silicon-bearing materials. So yeah, we all recognize that silicon is a value-added element for electronics manufacturing, but how do you actually get from the point where you can take waste glass, which contains all kinds of other impurities and contaminants, and get it to the point where it becomes a useful element to manufacture electronic products? And wouldn't it be nice if we could actually, in local levels, at council levels, not think about sort of transporting it out across to regions far away, but rather thinking about, well, okay, if we were to collect enough of these difficult materials in a particular region, could we actually start to see ourselves as raw material suppliers rather than waste generators? And I think that's the shift in mindset that we need to be able to think about. Because if we have the technology, we have the high-tech product at the end of the chain, we can certainly become raw material suppliers. Heck, we could even start to see ourselves as high-tech producers. So if we start to shift the game from, waste, a burden, a problem, to actually becoming raw material providers, to then moving down the value-added chain and creating silicon-bearing products, we're suddenly into niche high-tech manufacturing. And that's really sort of the vision of the future, that you don't have to. The nice thing about producing high-value, high-tech materials is that you don't have to depend upon large tonnages, because these types of materials are high-value, they're niche, you can do it on a small scale. So you can imagine the vision of the future could well be a scenario where at local levels, councils coming together with waste companies, with manufacturers, really creating these high-tech products of the future. And you're actually doing it on a scale that is feasible and doable. So effectively, the vision for the future should be, how should this factory of the future look like? So if we can start to almost imagine what that scenario in the future could look like, you could very well see various micro factories popping up in different regions. And every micro factory is a specialist in doing what they're doing. So, it's like sort of going off to a specialty bread shop and buying your specialty bread there, and going off to a specialty cake shop, because these guys know how to do what they do really well. You could imagine that you've got one region that's collecting all kinds of difficult glass, another region that's collecting all kinds of difficult types of polymers, which is just another type of plastic, but not all plastics are easily recyclable. You could imagine someone collecting all kinds of old CDs that have been left behind in everyone's homes. And if you start to make it more and more complex, you go someone collecting mobile phones in one region. So again, you can start to see that the scenarios in the future are going to require us to become much, much more creative and innovative in the way we treat these types of materials. I'll show you some pictures towards the end where you can actually start to see that you can take different types of mobile phones and electronic products and start to look at the kinds of high-tech copper alloys that we are producing. So could we be processing a lot of these different types of end-of-life products by actually tapping into the above-ground mines? So let me leave you with a bit of that vision, that what we are is owners of above-ground mines, and it's in our hands as to how we transform these above-ground mines into those high-tech products. And I think it'd be really, really super cool if we in Australia could lead the way and demonstrate to the rest of the world that this can be done. And so now this is not just a pipe dream of an academic at the university going, yeah, wouldn't it be nice to do that, because I've done a little experiment in my lab. This is actually reality now. We are actually using waste tires in the process of making steel, and that's where One Steel comes in. Our industry partner, One Steel, has actually demonstrated on a commercial scale in Sydney, in Melbourne, and we've implemented this technology in places like UK and South Korea, where our technology is actually helping the large manufacturers of the world to do environmentally sustainable steelmaking. And that's really the vision. We don't have to be the large manufacturers. We just have to be the smart manufacturers who know how to take on these types of end-of-life resources and create high-tech products. And that's indeed where credit has to go to industry partners like that of One Steel in this instance, who of course have the vision to partner with universities. And so collaboration can come from all sorts of different forms. They can be between academia, industry, councils, because everyone's got a role to play. And I think that's an important point. The other message that I wanted to probably leave you with is the opportunity for young people to feel that this is an exciting future. And not just to always be thinking about that, oh, well, gee, there's no more manufacturing happening in Australia. It's all doom and gloom. The realities are that if the paradigm shift in manufacturing sectors is coming along across the world, where we're going to be living in a resource-constrained society, well, here are resources. We're sitting on top of these resources that we need to be able to tap into, and young people need to be clever and innovative in looking at the science, technology of how we can actually transform these types of waste resources into high-tech materials. And that's where, of course, the whole team at the Smart Centre comes together in partnership with One Steel. So I want to just begin by putting up some of these images there for you. This is not just an Australian scenario or a challenge. This is a global challenge. And that's the reason why, of course, the kinds of technologies that we look at in transforming these types of resources becomes such an important goal for the future. So I wanted to just take a moment to show you, and I'll of course certainly show you this video as to how we go from waste, which is basically that, waste glass, into the alloy that you see on your right, which is the ferrosilicon alloy. So how can you go from something that's waste glass, plastics, and what do you actually do? But remember I said the critical elements there are the fact that you've actually got silicon present in glass. You can take a whole lot of waste iron oxide and plastics, and yes, voila. No, and it's not magic, because I'm not a magician. You do end up producing ferrosilicon alloys. And you might say, well, gee, The world cares about ferrosilicon alloys because it's got a whole range of high-tech applications. And the list goes on and on. So that's really one example of how we can actually create these high-tech alloys and transform and be a supplier and really be shipping out the high-tech alloys to the world. And let's face it, making a whole lot more money for our manufacturing sectors. What does all of that mean? It is effectively looking at diversification of the economy in the future, because it's not going to be business as usual in the future, as we keep hearing. And of course, everyone keeps asking, so where to? So what's the next step? And we could be playing a significant role in shaping that next step in the future. Well, what else can we do? So to throw you some examples here. Here is an example of silicon carbide nanoparticles that we produce by using silica, so that comes from glass. And we actually use, in this particular instance, waste CDs. So we've taken waste CDs, we've reacted these at high enough temperatures, and you've got images that show you. And a lot of scientific work that we've done has been published in the open literature, so there is information for people who want to go and read the details of how we get there. But you might say, well, okay, so what's such a big deal about silicon carbide? These are, again, examples of high-tech materials. They need silicon and carbon. CDs provide significant levels of carbon. So it's not just CDs, it's a whole range of other types of plastics and polymers that we traditionally will end up putting into landfill because they're not recycled in a traditional way. What else can we do? Well, here's another example of things that you all recognize. On the left-hand side, e-waste. So electronic waste that has got a whole array of incredibly fantastic materials. So of course, there's the obvious copper and tin and so on that we're used to. But also remember, there are other things and we're only focusing here on this particular example, looking at printed circuit boards. So basically the heart and the guts of any electronic device that, of course, different types of devices have. So they'll have integrated circuits. They'll have basically a lot of the wiring, copper, soldering, tin, and so on. And then they've got the actual substrates, the green substrates that you see. These all contain different types of plastics. They might even be reinforced with glass fibers, so they contain some glass. So you can suddenly start to see that there is a whole lot of opportunity for us to be able to convert that into high-tech alloys. So what have we done? We've actually produced these types of alloys in this instance. Of course, what you see in that picture there are some examples of red droplets and some examples of white droplets. The red droplets are copper-rich, the white droplets are tin-rich. Wouldn't it be nice if we could be able to tell the rest of the world, it's okay, you may not need to mine copper from the ground, because guess what? We've actually got a concentrated resource of things like copper in our electronic devices. And we might sit on top of all of these waste materials and be sending it to the rest of the world, which may well be the biggest mistake we do, because guess what? These types of resources contain 10% at least of that order of copper. And what does an ore contain? Less than 1% of copper. So we're effectively saying we've got a resource that contains 10 times more copper, highly valuable metal, but yet we might not be tapping into it. So it's a bit of a shame. And I guess that's why I'm here today, to be able to effectively throw a whole lot of ideas and to say that science is progressing, things are happening. We want to be able to take the leadership in Australia to be able to show to the rest of the world how we can actually go from what we see as a waste on one side to highly valuable metal and metal alloys on the other side. We don't have to sit back and cry that, oh, gee whiz, the mining boom is over, and, what are we going to do next? Well, actually, as I said to you, this is a whole new kind of mine, right? It is an above-ground mine. The question is, the world doesn't know how to tap into these types of high-tech alloys of copper, silicon, and so on and on. If we know in Australia how to do it, if the science and technology has been supported, if new innovative solutions are being developed here, that's really where I think, as councils, as partners, we all need to come together and go, we can be resource providers. Effectively, we're suppliers of raw materials. And of course, manufacturers need to come together to be able to produce these types of outputs. What that leads to, of course, is the whole new concept of green manufacturing. So our concept of green manufacturing is something that is not just a pipe dream or a vision that's out there in the future. It is happening right now. The reason why we've used rubber tires and used that in the process of making steel, the example I gave you earlier, is because these types of rubber tires contain carbon and hydrogen. Hydrogen is a fabulously clean element that can actually be used in the process of making steel. It actually reduces that iron oxide into a metallic form. So you can actually make steel by effectively using hydrogen as the reductant. So there are a whole lot of new discoveries there that actually point to the fact that there are elements locked in these types of waste resources, and in case of tires, it's carbon and hydrogen, that enable us to produce these types of high-tech alloys. So, of course, the reason why we're doing this is, as I've shown you examples, the complex materials we're dealing with, whether it's e-waste or, auto waste, the glasses that come out of cars, architectural glass, waste that comes out of buildings, refurb, and so on. These are all complex materials. We don't have this nice clean stream of, here's a bottle, here's a plastic bottle, let's convert it into another plastic bottle. Life's never going to be as simple as that, because we want our products to be really functional. We want them to do the things that we're just getting used to. We demand that of our products. So I would probably throw at you, if we can demand that of our products, why can't we demand that of our end-of-life processing, where we take our complex e-waste and say, you know what, we can actually transform those into high-value opportunities. And that's really the whole idea here, is to be able to be very innovative and look at waste as an opportunity to transform it into value, which then means that new science has to be developed. And of course, Australia leads the way in terms of these scientific developments. Can we actually all come together? And this is the right time when we should be doing that, when we should be at the local level, creating these opportunities and transforming it into high-value alloys. So why do I say some plastics are not recyclable? Here's an example of something that you might not have attributed it to being a plastic. Well, it's not a traditional plastic. Bakelite, in a lot of these applications, is a thermoset plastic. And what I mean by that is that you can't simply melt it down and create another product that looks exactly the same. Some plastics you can melt down, so when you've got bottles like PET, you can actually melt those down and create new bottles out of them. But when you actually have complex materials like these polymers, you can't actually melt it down and create new products. So what do you do then? Okay, well, this is where you break it down to that elemental level. You go, okay, well, what does it actually contain? And no, I'm not going to scare you with the Chemistry 101 lecture telling you about the molecular structure, except just to point out that you've got carbon, hydrogen, oxygen in these types of materials. So again, you can either see it as a plastic or a polymer that ends up in landfill, or you can see it as a fantastic resource of carbon, hydrogen, and oxygen. As I said earlier, you've got enormous opportunities here to transform these into things like hydrogen molecule, CO molecule. The reason why this molecular transformation is so important to think about and not see it as a plastic is because you then can use these types of molecules in completely different ways. So the fact that we've been able to use tires in the process of making steel is because hydrogen molecules coming out of tires have helped us in steel manufacturing. And that's the whole reason why it's important to look at that. What else do you have in bakelite? Well, you've got carbon. Okay, so you might say, well, so what? Well, carbon in its own right is, again, a highly value-added element, as long as it's got the right kind of properties and it doesn't end up in the atmosphere. Because clearly the last thing we want is carbon to be released into the atmosphere and cause all kinds of other greenhouse gas emissions. What we actually want is for it to become into a high-value output. The picture here actually shows you is that you can transform these types of complex polymers into high surface area carbon-bearing products. So you've got measurements of surface area, and you can then start to think about, could we then produce activated carbon? Could we produce carbon for making electronic products? Are there carbon anodes? Are there materials that are fantastic in terms of their electronic properties? And guess what? You can do that out of carbon. And that's really the whole idea, that you can take these types of waste materials, understand where the transformation is occurring, produce these high-tech materials, and you can go and buy right now in the marketplace carbons, high-tech carbons, that will cost you of the order of about $1,000, $2,000 a ton. So you're not talking about something that's not valued in the marketplace. So, and it's not about, well, we've got to worry about creating a whole new market. The reality is that the market exists for these types of high-tech products. It's how you actually take these types of waste materials and transform their properties. Do you transform it in a way that it becomes highly conducting? From an electronic point of view, do you transform it in a way that it's got high surface area, as this image shows you? That's where the science comes in. You can't just sort of sit there and go, well, I'll just make all of these products out there and it's easy to do. I'm not saying it's easy to do. If it was easy to do, everyone would have done it by now. The reality is that we need to understand how we transform, and scientifically, how do you get from that waste resource to these types of high-tech materials? So moving forward, basically what we are saying is that the 3 Rs are not really going to be sufficient in terms of dealing with the future challenges. What we have to ask is, what is this 4th R that we're calling reform? So quite simply, the 4th R is basically saying that if the 3 Rs are not going to take care of the waste resources that we are generating as a nation and as a society as a whole globally, well, then what we should be saying is, let's not waste our time and effort into starting to separate bits of plastic and bits of metal and bits of glass, because let's face it, it's never going to be economically viable. You're never going to return it back to the original properties of the material. What you really want to do is you want to be able to understand at that elemental level, at the molecular level, what are you producing, what are you generating that's got high value, so that you can effectively make value-added products and, let's face it, sustain a manufacturing industry that doesn't require economies of scale. So we don't have to think about these large tonnages. We can actually think about economies of scope. And I think the whole mindset has to shift from that traditional mega factories where we always think about manufacturing at a large scale, because let's face it, we've been told, manufacturing has to happen on a large scale, and we need economies of scale. And I'm here to challenge that sort of thinking, that it doesn't always have to be that way. It can be around small scale factories that are not always the mega factories that we've been used to, but rather micro factories. And what these micro factories should be doing is producing these types of high-tech materials, because we understand what the science is all about. And I think that's the important message. So if we are innovating, we should be able to do these types of transformation right here in Australia, and that's really what the Smart Centre does. We develop the science, of course. From our perspective, it's not just about giving up on the technologies of today. So it's not about saying, well, let's shut down the steel plants of today because, let's face it, they're energy guzzling, factories, but rather to help steel producers and other producers to be able to say, how can we become really smart? And indeed, that's a reason why our technology of using waste tires in the process of making steel is something that's attractive to steel producers worldwide. Because let's face it, it's not just us. Everybody wants to reduce their energy bills. Everybody wants to be able to reduce the cost of manufacturing. So these types of technologies are going to help and sustain technologies of today to transform into technologies of the future. And of course, down the path, we are going to create green manufacturing solutions coming out of these types of research activities. And as I also said, it is about working in partnership and developing human capital. Let's face it, again, where are the people? It's all of us in the room here, but we also have a responsibility towards teaching future generations of scientists, engineers, professionals as to what this business actually could look like in the future. And it's an exciting future, and we've got to take home a positive message from this. So the innovation and collaboration is something that we have been working in implementing new ideas. These partnerships have allowed us to not only transform the industrial landscape of what we are doing in Australia, and indeed, of course, being able to recycle waste tires, if we have to do it in a way that we truly create impact, then we have to be able to transform it on a large scale. So recent milestone that we have achieved in partnership with One Steel is we have actually recycled more than 2 million tires and use that in the process of making steel right here in Australia. So that's, again, a landmark that can be achieved. We're exporting these types of innovative solutions, and that's important as well. Just a bit of an image here of what type of industry partners we have. As I said, it's not just about manufacturers in Australia, it's also about our international partners who we work with, all the way from Australia to LKAB, a Swedish mining company. So it sort of gives you the full spectrum of opportunities across the world where there's an interest. So I'll skip through some of these images because we've talked about it, and you can, I guess, think about what might be an important thing to focus on from your local region. So whether they happen to be the Bakelite heat insulating handles coming out of frying pans, which I'm sure we all have at home, and you know, they often fall apart and you go, what do I do with this? To your melamine, very fancy, sophisticated dishware that I know I use at home as well. You know, with kids, it's nice to have that rather than give them the really expensive glassware. To a lot of the things that we use in our daily lives that we're used to, whether it's the old CDs collecting at home or indeed the architectural products. So the other important message, of course, here is that the reason why we've got to do all of this is, let's face it, there are so many different types of plastics being used, mixed with glass, mixed with different types of metals, where the reality is we've got to say, you know what, we're never going to be able to separate these different types of materials out. So we are rethinking a lot of these opportunities. The benefits for steel producers, because I've mentioned that so often, is also not just the environmental benefits, but economically it is a good thing for them to do because it does save on consumption of raw materials and cost of electricity. So as I said, we have indeed transformed these tires into steel products, and we keep ticking away the clock in terms of the number of tires. Back when this slide was produced was 1.5 million tires. We've now crossed the 2 million tire mark. So I guess I wanted to just be able to take you through the video that I promised. I know time is short, so I'm going to try and wrap it up. A lot of these images just show you how we've actually produced ferrosilicon alloys. And just as the video's coming up on the screen, what you're about to look at is basically looking into a high temperature furnace that we have in the lab. We've got a combination of glass and plastics. We've made that into a pellet. This pellet has got a combination of oxides, like I said, with glass. It's silica, some iron oxide, waste materials, of course, and waste plastics. The pellet has just entered the furnace. The furnace is sitting at 1550 degrees Celsius. What you're about to see in front of your eyes is the actual transformation into these types of high-tech ferrosilicon alloys that I was referring to earlier. So you can see the chemical reactions are taking place, and of course, the reduction phenomenon where the oxide is getting reduced into a metallic form is happening because you're actually getting the oxygen out from these oxides and you're actually converting that waste silica, which is a combination of silicon and oxygen, into a metallic output. And this iron and silicon that are both metallic outputs from here are combining together to form a ferrosilicon alloy. And so the reality of what you're seeing in front of your eyes there is that these types of high temperature reactions and transformations are all as a result of the scientific developments that are taking place at the Smart Center, and we are indeed able to show you that there is no such challenge that we cannot take on. And I think it all comes down to understanding scientifically how we transform these molecules. And I'll just move forward because time is short. But I think a lot of these types of results are showing you that the recoveries of silicon, I mean, these are commercial grade alloys. When we talk about 30–40% silicon weight in these ferrosilicon alloys, for instance, these are all commercial grade alloys. They, of course, used in a whole range of different applications. And again, I will wrap up fairly quickly because I know time is short, but I wanted to run through some of these images just to be able to show you that scientifically you've got to go in, zoom in at the molecular level, and that's why a lot of the scientific tools that are used, X-ray diffraction and so on, help us produce these high-tech materials, whether they are metallic ones, the ferrosilicon ones we talked about, or in this instance, a ceramic particle of silicon carbide. They are all used in different high-tech applications. Silicon carbide is a fantastic abrasive material, for instance. And of course, its applications are simply mind-boggling because of its quite special properties. Have we gone off and done some of the other types of ceramic materials? I wanted to again show you some pictures of what kinds of nanocomposites we're producing. And what's quite fascinating is that these are all coming out of end-of-life waste materials. Here's an example of a composite of silicon carbide and nitride. And you can again start to see right in front of your eyes there that there are some fairly highly specialized materials, materials for which the market exists, and of course moving forward into the more complex demands of materials at the nano and the micro level, we are actually going to be able to produce these kinds of niche outputs. You might say, well, who cares about these types of nanoparticles? Well, they have some pretty special properties. I mentioned about abrasive properties, their strength, they've, wear resistance. So again, the list goes on. And then, of course, we don't all need to be reminded the challenges of the day-to-day things that we see at home, whether it's a bike part that you see made out of carbon fiber. So there's carbon composite bike parts there. There's metallized plastics, again, things that I'm sure you've all sort of looked at and go, wonder what we do with this? It's neither a plastic nor a metal. What we've actually shown is that the combination of the two together, the kind of plastic and the metal that comes in these metallized plastics, have got actually some pretty unique properties. And putting the two together, we can actually create some fairly fancy and amazing alloys and products. So again, opportunities rather than an environmental burden is the way I would see a lot of these types of materials. So look, I'm going to sort of skip through a lot of these slides at the end. There's a lot of scientific detail that's there for you to look at, videos that ABC has covered over a period of time, if you were ever interested in following through with these details. But I'll finish off at the end by coming back and showing you, I guess, some of these pictures of what, of course, and not that I need to show you what a circuit board looks like, but it just sort of gives you a sense of, what opportunities exist when you look at a lot of these types of materials. So can we actually do it is the question, and there it is. The evidence right there in front of your eyes. You've got different types of metallic outputs that are being produced from these types of waste materials. You can see copper-rich alloys, the reddish ones. I love those. They look absolutely fantastic. And of course, the white tin-based alloys. And of course, the opportunities are just endless right there. You can see going from something that looks pretty useless and hopeless on one side to, on the other hand, at certain right temperatures, you can indeed produce some fairly dramatic structures. And you can see the foam-based structures that we are producing. And that's the reason why we can indeed have a lot of these materials doing some pretty special things. So I'm going to just finish off here and leave you with some thoughts that complex waste materials can indeed be transformed into high-tech products, which of course can lead to environmental and economic benefits. And I suppose what it means is that perhaps what we should be thinking about is that fourth R of reform, which enables us to add value, truly economic value, to the kinds of waste materials. But we can certainly achieve the value-added green materials that we are already showing is certainly possible. So thank you very much for your time this morning and appreciate it. Thank you.